Trig identities or trigonometric identities are, I'd say, both a unit and a topic. In this course, I deal with 28 or 29 trigonometric identities. I am not giving you those 28 or 29 today. There are all sorts of sheets online that will give you a ton of trig identities. So this is the one I've cut and pasted into the Smartboard document. You could print it off if you wanted to, but it's very unnecessary. We don't deal with all of these. In fact, in my life as a math student at high school or university, I didn't use a lot of these, but they do exist. Another thing I've done is I've left you with this link, SOS Math. Here's a table of trig identities. We are going to use a lot of these. Again, not all of them. And at the bottom, it says download as a PDF file, so you could potentially download a pretty version of that. Going back to the one that I provide as part of the Smartboard document, we're going to cover tangent identities today, and we're going to cover reciprocal identities today, and we're going to cover 9 Pythagorean identities today. So that's 2, 4, 6, 8, and 9 more, so we'll have 17 today. We eventually look at the double angle identities in this course as well, and we look at the sum difference identities. Something that you've looked at already in your life in grade 10 and 11 math is the sine law and the cosine law, which are identities as well. So identities are equations that are always true. So it is always true that a squared equals b squared plus c squared minus 2bc cos of an angle. That's always true. Basically, trig identities are statements that are always true and include trig. So either sine ratio, cos ratio, tan ratio, cosecant, secant, or cotangent. So we build all of those into it. What I'm going to do, and this is going to take up a bit of time before we actually start doing what we're supposed to do with trig identities, is someday, even though there are all sorts of lists on the internet, someday you may have a teacher, whether it's calculus and vectors next semester if you're taking that, or if you're going on and taking a calculus class at university, college, trade school, you may have a teacher that asks you to memorize all of these. So what I'm doing is I'm providing maybe a way that you can memorize them. I have memorized all 17 today. Mostly because I have the mechanics of what I'm going to show you on the next 2 slides I think it'll take. So I'm also going to label the different identities, because if this is an assignment to make yourself a resource sheet, you may find it handy to label the information. So I will possibly go off to the side and do some little scribbleland stuff, not the same as the stuff with the trig graphing, but similar. So, I'm going to do this stuff in black, and the first ones we're going to look at are the reciprocal identities. So I am going to list 6 reciprocal identities. And it's been a couple of days since I've wrote on this tablet, so bear with me getting used to it again. So, that's 3 of them. This is not. That's 3 of them there. And the other 3 are the reciprocals of these. So sine, theta, sine, cos, tan, cosecant, secant, cotangent all have to have an angle positioned after them. You can choose x, you can choose theta, you can choose y, you can choose beta. There's a whole heap of things that you could pick. I'm using theta for the purposes of this note, and sine theta is equal to 1 over cosecant theta. So this box is one of the 6 that need to go on your resource sheet. Memorize them if possible. And you might notice that it's not a heck of a lot different than this one. So those two are linked together, so I don't have much problem. If I memorize one of them, I can actually get the other. Next one, and you may be able to start predicting here, cos theta is equal to 1 over secant theta. So those two are linked together. I'll put a box around this. And the last one, let's see you predict. Tan theta is equal to 1 over cotangent theta. I am well aware that you may have very little experience with some of these reciprocal identities. First one, a thing I want to write down is these are the prime... Oh, not yet. Sorry, my bad. I'm not done talking about reciprocal identities, mostly because I know that you may not have all the experience you would benefit from for the reciprocal identities. So I just want to remind you what exactly it means. So I'm going to do that in red down here. We're not done, but we're done reciprocal identities. Those are the 6 of them. Sorry for making my little yellow bubble go all over the place. So those are the 6 reciprocal identities. So my scribble is that hopefully you remember that sine theta is opposite over hypotenuse. And hopefully you realize or remember that cosine theta is adjacent over hypotenuse. And tan or tangent theta is opposite over adjacent. So I've sort of written them out here and then abbreviated in this case, but I've written sine in full, still with a theta, cosine in full with a theta, and tangent in full with a theta. What your experience might not include is that these 3 right here are called primary, this is what I thought I was writing before, trig ratios. So what that means is they are the first 3, so they're the important guys, sort of like the primary colors make up all the other ones. So everything comes from these. They're trigonometry and they're ratios, meaning a fraction of information giving you more information. The next set are not primary trig ratios, they're secondary trig ratios, and that is cosecant, spelled in full like that, still theta, and because they're reciprocals, that just is a fancy way of saying upside down. So cosecant theta is h over o instead of o over h, which is why this is its identity. The next one is secant theta, h over a, and fortunately cotangent and tangent go together quite naturally. Guess? A over O. So what I tended to remember in high school, that's just kind of fallen into my brain naturally now, is that the C's and the S's don't go together for these two, but the tangents go together. And just to make this complete, I'll dig out the blue pen and write what I said I was going to write, and that is these are the secondary trig ratios. Now I am going to take this to a new slide because I'm still not done. Come on. Oh. And the reason I'm not done is because if I go back to any one of the 6 boxes that are the 6 reciprocal identities you're responsible for knowing, there are some subtle changes that can happen with any of them. So I am going to talk about this first one, and because they're all built the same, as in something theta equals 1 over something theta, every single one of them. I'm going to deal with this one and tell you some extra facts about it. Like the fact, and even though I'm writing in black, it doesn't mean that it's supposed to be memorized. First of all, that sine squared theta is 1 over cosecant squared theta. And sine squared theta, because this is squared, means that you square everything on the other side. So that's why the cosecant is squared, and 1 squared is 1, so you don't even notice that. If you have forgotten or never knew, sine squared is like this, and I guess technically it should be abbreviated to that, but somebody decided to abbreviate an abbreviation and write it like that. Now, what is not true is this. You cannot make that 2 slide down and be big. This is not the same thing. So this will also work. Let me use cotangent just for kicks. This will also work for any of the other ones and any other number. So if I decide to cube cotangent theta, I'm cubing 1, which says 1, and I'm cubing tangent, which means it's visible. So that's just a little bit of extra information. In all of this, these are the 6 that you need to know how to work with, and the extensions of that. The ratios are important as well a little bit, but I'm kind of hoping you had these locked into your brain when you left grade 10. All right, next up, not all of these, let's look at this one. So I'm going to write this in red, and these are the quotient identities. So I hope you have a tiny little memory still in your brain about long or synthetic division. And when you came up with that answer, it was called the quotient. So quotient is a fancy way of saying the answer to division. So there's 2 of them. I've given you 1 right there. And the second one is cotangent. So if I look back a slide, you'll remember that cotangent and tangent are upside downs of one another. They are reciprocals. So it goes with a little bit of logic that cotangent and tangent are the upside downs or reciprocals here. So those are the 2 quotient identities. Now, just like before, so just like with the reciprocal identities, if I take tangent and I square it, I need to visibly square all of those, so the other 2. And if I take cotangent and I put it to the power of 5, I have to do that with all of them. Unlike these ones where you think you forgot a spot but didn't because it's a 1. All right, I'm going to take a little break because I've got a bit of a hand cramp, and we're going to look at these ones. So if I go back to the green sheet just before I take my break, there are 3 here. I think it's worth having 9 on a resource sheet if you're allowed to have a resource sheet, which for me you are. So I'm going to put this here, and I'm going to drag these guys down the page because we're not going to deal with them quite yet. Everything comes from this one, and this one is called one of my 9 almost wrote theorem there, Pythagorean identities. Now, if I mark a resource sheet on you, it will be your responsibility to put 9, even though almost every single sheet has 3, because that will be my criteria for your resource sheet. Okay? And on top of that, you shouldn't whine because I'm giving you extra resources. So don't even start. So I am going to pause for a sec. All right, Pythagorean identity time. This dot out of there. Okay, so the first 3 of the 9 Pythagorean identities I think is fairly easy. I'm still going to keep putting them in black boxes so they stand out. So the first of the 3 trig identities is this one. This is easily my favorite Pythagorean identity. In fact, it's my favorite identity overall, and the reason I love this one so much is it takes trig and it turns it into non-trig, and I quite like that. The thing about this is that if I change it to something else, but maybe follow what looks like a similar pattern, this is garbage. This is not a thing. So your Pythagorean identity is fairly locked in. It says sine squared of an angle plus cos squared of an angle is equal to 1. Now, I'm going to leave this here just for a second. For some reason, I can't get rid of this cross. The reason this is not a Pythagorean identity, my handwritten one, the reason that's not a Pythagorean identity is because it doesn't look like Pythagorean theorem. Pythagorean theorem says a squared plus b squared equals c squared. Here's your a squared plus your b squared equals your c squared, and 1 squared is 1. So this is very Pythagorean. 4s do not make Pythagorean theorem. So let's get the 4s out of there. Let's make our other 2, though. And these are quite easy, I think. Number 1 is taking sine squared theta and leaving it on the left-hand side of the equal sign, leaving the 1 on the right-hand side of the equal sign, and taking the cos squared theta, which is positive, across the equal sign and changing its operation. And I think that is a very useful second Pythagorean identity, even though it's not all that different. It's nice to have it written on the page. So that's my number 2 or 3. The other one is just the other direction, as in leaving the cos squared on one side of the equal sign and bringing the sine squared over to join the 1. Another thing I want to say just before we move on to the next batch of 3 is if you do this, that's also garbage. You need something to be taking the cos or sine of. So it's got to be a theta, an x, a beta, a y, an m. A number is okay, although with identities you normally don't get numbers. So let's get this out of there. So that's my first 3. Now I'm going to draw a line, even though I'm not done Pythagorean identities. But I want you to know that I actually only have this, my favorite, one memorized. So I have 1, 2, 3 of them memorized. These 3 I just flip. I have 2 more memorized, so that's 5. And I have this one, so 6. So out of the 17 identities I'm giving you today, I only know 6 of them, and the other ones I make up as I go. As in, I make these 3 because I've memorized those. I make these 2 because I've memorized this one, and I can do algebra. So the other 2, which means other 6, the other 2 that happen come from my favorite. So let's see which one we get first. I can't promise. It's just me doing math. So the first thing I want to do is I want to write down, and I'm going to do this in blue. I'm going to write down my favorite, the base Pythagorean identity. And what I'm going to choose to do is I'm going to choose to use sine squared theta. So I'm going to divide all three terms by sine squared theta. And then I'm going to make it look pretty. So for instance, sine squared theta divided by sine squared theta is 1. Cos squared theta divided by sine squared theta is this one, but the cotangent is squared. And 1 over sine squared theta is sort of right here, so that's going to be cosecant squared. And even though I'm saying them wrong, every time I write them, I remember to put in a value. And yes, you have to choose the same letter, whether it's Greek or our alphabet. You have to use the same letter, the length of the Pythagorean identity. So there is this one. So I have generated that and not needed to memorize it. My brain doesn't hold that information. And then all I do to make the other two is what I did with the Pythagorean identities up above, and that is do a little algebra. So I'm going to leave the 1 behind, cosecant squared theta, and bring the cotangent over. And there's number 4 and 5. And then I'm going to do the backwards of it. Leave cotangent squared theta behind. Leave cosecant squared theta behind. And pull the 1, which is positive, over to become negative. So there's 3 more, so that's a grand total of 6. I'm going to draw my line. Not a very good line. And I'm going to hopefully generate that guy. So again, I am going to start with my favorite. And this time, instead of dividing by sine squared theta, the length of it, I am going to divide by cos squared theta. I mean, let's face it, if we choose the other one, which is a 1, we're not doing anything at all. So now I go looking for my replacements, which is actually what trig identities are all about. So sine squared theta over cos squared theta, that's this, but squared, so I'm going to steal the other side, tan theta, but squared. Cos squared theta divided by cos squared theta is 1. And from the reciprocal identities, here's what I'm looking at. So I've squared both of those. So this is actually secant squared theta. And we've generated that one without actually memorizing it. Now, if you can memorize this stuff, knock yourself out. I'd be super happy. But it's just not possible with my brain. So there's number 7, 8. And finally, leave the 1 behind, leave the secant squared theta where it is, bring the tan squared theta over. So if I've given you the ability to use a resource sheet, what I expect is the 28 or 29 identities, but right now you could list off 17 of them. these 6, 2 more, so 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And if I am marking your resource sheet, if you make any typos, you lose a mark, because this is this would be a copying exercise, and I want the ability to correct your work before you go into a test or exam situation and use wrong information. So if I find you do this and don't have the squared, I will correct it, but I will take off a mark. If I find that you don't have the squared and a theta, that's still 1 mark, but you do need both of them. You need all of these identities to be 100% correct, so that when you go to use them, you are 100% correct. So I'm going to take a little break and come back at you with this list. So if you are a list writer, I think that right now is a great place to pause this and write them down. That's your chance. Sorry, that was a bit extended, especially since I'm just going to talk and not actually do a whole lot of writing right now. But I found this list online, so I totally cut and pasted it. It's from the int math website that I used for the biorhythms. These are suggestions, so that doesn't mean they're steps to proving trig identities. I'm going to go over them and maybe refer back to them a bit later. But this one I agree with. If you, and it's also British, so it's got a bit of spelling differences and word order differences. So it says, learn well the formulas given above. So if you know your 17 identities, you don't have to go searching every time to see if you can use one. So learning them well is actually a really good suggestion. I'm not saying you have to memorize them. Someday you might, but knowing that, you know, this kind of looks like something that reminds me of what's on my page might be a direction that you go in. So it says the better you know the basic identities, the easier it will be to recognize what's going on in the problems. And that is absolutely true. I don't believe that number 2 is something that you should follow. It says work on the most complex side and simplify it so it is the same form as the simplest side. And also, where's the other one? Don't assume the identity to prove the identity. This means don't work on both sides of the equals side, equal sign, and try to meet in the middle. Start on one side and make it look like the other side. I don't necessarily agree with these, and I'll show you why eventually. Once I go through this. Many of these come out quite easily if you express everything on the most complex side in terms of sine and cosine only. And that is absolutely true. If you think back to the graphing unit, sine and cosine was your friends, or were your friends. It's pretty much true here. It's not always true. It's pretty much true in trig identities that sine and cosine are also your friends. That is not on the most complex side. It's on both sides. And here is a good tip. In most examples where you see a power of 2, that means you're probably going to use one of the 9 identities that we made for Pythagorean identities. That's just a little tip. Not necessarily 100% true, but pretty close. So let's look at what trig identities look like. I've got a bunch of them, which is why this becomes so long. I may do a couple of questions twice, and the reason for that is I want you to know there isn't only one solution to trig identities. Hopefully you find the quickest way, but that is not always going to be the case. And unfortunately, I will have to bop back and forth, so a reminder again that you can pause and take little breaks or rewind if you need to. Now is also a good time to take a break, and if you're a list writer, write that list if you didn't before, or make sure you have the 17 identities sitting in one place. So I have the 17 identities spread across 2 smartboard slides. That's not ideal for the purposes of what we're going to do, so maybe consolidating them is a good idea. So here's the first question. it says, prove that tan y over sine y is equal to secant y. Now the thing is, if I refer back to the list, it says don't assume the identity to prove the identity. I actually want you to assume it because I am asking you to prove that. So this is a true statement. You must prove that it's a true statement by making the left side and the right side look identical. However, you can't assume that it's true the length of your work. You have to just keep it in the back of your mind. You might run into a textbook or teacher or professor that says prove if possible. You do not like that person. You do not like that textbook because maybe it's possible, maybe it isn't. In my class, you will be asked to prove things that can be proven. The next thing is I remind you that sine and cosine are your friends. So what you want to do, and if the y isn't something you like, then definitely change it. So I don't particularly like y, so I'm going to turn it into x's. You are totally allowed to do this as long as you do it the length of the question. So you have to do it on left side, right side, entire left side, entire right side. So you need to try to make the left side, which has to stay separate from the right side, you have to make these look the same. So you have to go back into your list of 17 and find something that will replace anything on either one of these sides. But you do have to keep it completely separate. So the thing I know is that secant x can be replaced with 1 over cos x. So you have a list of replacements. I know that tan x can be replaced with sine x over cos x. And I really don't want to put a triple, oh, that's bad. Make sure you make all adjustments well. And then I don't really want to go over sine x. So instead of doing that, I'm going to do this. Now the thing that pretty much screws people up about trig identities is if you can't do these skills with numbers or maybe even letters, then doing it with trig is quite difficult. So hopefully I work through this stuff slowly enough that you can fill in some blanks. But I know that this is over 1, and I know that division of fractions doesn't truly exist. Instead, I'm going to take this one, and I'm going to use a dot instead of an x because my x's are used up, and I'm going to make it 1 over sine x. Now somewhere in this list, I'm pretty sure it says don't look at both sides at the same time. No, it says work on the most complex side and simplify it so it has the same form as the simplest side. We didn't do that. We took the simpler side and did something to it and then changed. You can bop back and forth as long as you treat it like 2 separate questions. And I always take whatever side I'm looking at and I keep gazing over at the other side to see if I'm even close. So this is a roadmap. It's kind of telling you, oh, I need to get there. So hopefully you can see that because this is all multiplying and dividing, you can knock this sine x from the denominator with this sine x from the numerator, and what's left is 1 over cos x, and you should not be surprised that they are the same. And once they are exactly the same, you can do one of many things. You can sum it up with therefore left side equals right side. I like to put a happy face. I'm happy it's done. You could put QED, which is Latin for that which is proven, or like I like to say, this is done. And I've also seen diagonal lines that are slightly in descending lengths to say that this is over. So you have lots of choices. I usually go with the top 2. You could just put a happy face. You could just put a left side equals right side. What you can't do, for those of you who think you're hilarious, what you can't do is this. I know I said it's true from the very top, but you can't just say, therefore, left side equals right side. Yeah, I know. That's just me being kind. So you actually have to show all the work to be able to say the left side equals right side, or a happy face, or a QED, or this. This question, I can only think off the top of my head that there's one way to do it, and it's the way we did it. So let's move on to a second question. There it is. So I think this is one I like to do twice. So I am going to pause this for a second and move that other question over and clone this so I can do a second method down below. So give me a sec for a technological break. So I hate to tell you that the only way that I've gotten good at proving left side equals right side with trig identities is by practicing it. If you are able to do this entire unit without doing a whole lot of work, then you are quite amazing and should probably go into straight maths. This is difficult stuff. It's not natural, so if you pick up these patterns, you deserve a little pat on the back. However, having said all that, that statement is not a dare. You probably should do this old school and make sure that you practice, especially if you are trying to get yourself ready for college, university, trade school, where nobody's gonna baby you or care if you get stuff. So, like I said, I have taken this downstairs. I hope you realize that my numbering system is often off. So that first question, example 1, yay me. This question, example 2, yay me. This one, example 3, and then I go back to 1. So regardless of the order. So I'm all over the map where I steal my questions from, and I don't change my numbering. So you can change it as you go if necessary. So there's my first sentence, or my first setup, sorry. And I'm going to go over to the right side first because it's only one piece of information. So my decision making is actually less on the right than it is on the left. And I recognize that as one of my reciprocal identities. So I'm going to replace cosecant x with 1 over sine x. And as you can see, I did change my y's to x's. So here we go. Now, I can't think of anything else to do on the right-hand side, so I'm going to go over to the left-hand side and try to work myself over there. That looks like it could be tough because this is 2 terms. My second term is pretty ugly, so this might not be easy. So the first thing I want to do is realize that sines and coses are my friends. So that term and the beginning of this term are really nice. And with cotangent, I could pick this replacement, which doesn't really help with the sines and cosines are your friends, or I could more wisely pick this one. So I'm going to pick cos whatever over sine whatever. I don't think it's that easy though. Nope, it's squared. So cos squared whatever, it's an x, over sine squared whatever, it's an x. Another thing I hope you know is that you have to deal with all of this because BEDMAS still works even in trig identities. So you have to do the multiplying before the adding. So I'm going to leave this sine x sitting here. And I'm going to put a 1 under the sine x because now we have 2 fractions and we can multiply across the top, multiply across the bottom. I'm going to do this in extra steps, so hopefully it's easier to follow. So sine x times cos squared x multiplied together over 1 times sine squared x. I can cross out one of these with one of these. make this a little bit smaller and move it out of the way for a sec. And then I'll have sine x plus cos squared x over a single sine x. And that doesn't look a whole lot like the right-hand side, but at least it's got the sine x on the bottom, whereas before it did not. Now comes a time where I go back to something I've showed you before, if you've followed through my notes. So these are two fractions, and they need to be added together, so that means I need to make a common denominator. And again, I remind you, some of you can't do common denominators with numbers, and you can't do common denominators with rational variable expressions, so you have to fall back on another approach that gets you there. So that was back in rational inequalities. I taught you the 1, 2, 3 thing. So 1, multiply those two things together. So that's 1 times sine x is sine x. So will you look at that? We're heading in the right direction. 2 was multiplying the bottom right with the top left. So always in that order. So that's sine x times sine x, which is sine squared x. Then I'm going to put down the plus sign, and I cross in the other direction as my 3 for the 1, 2, 3. And that's 1 times cos squared x, which is cos squared x. And you need to ask yourself, okay, so I'm super happy about this sine x on the bottom because of the sine x on the bottom of the right, but how on earth am I going to get this hideous numerator to be just the number 1? And the answer is my favorite. There it is, sine squared of an angle plus cos squared of the same angle equals 1. So I just get to replace it, because guess what? It's true. You just have to find your way there. So now I can move this out of the way for our second method. They look exactly the same on the left and on the right. So I'm going to give it my favorite summation, which is that. So like I said, there is often a second way of doing a question, and this is one of them. And someday you might be able to look at this. Maybe that day is today, maybe that day is tomorrow, maybe that day is, if you keep doing this stuff, a month from now, or maybe a year from now. But someday you might look at this and say, oh, I can totally see two ways of doing this question. At this point, I'm sort of expecting that you look at the questions and barely see one way. So that's just a guess on my part. I hope I'm wrong. Now, when I say that, I do want you to know that I can't think of anything else to do on the right-hand side other than that. I mean, there's really no other choice. There's no other cosecants on here except in here where they're squared, and that I think would just make it worse. So yeah, I'm not going there. It's the right-hand side. So what I hope you notice about the right-hand side today or some other day is that you've got two terms. You've got a term here before the plus sign and a term here after the plus sign. And in both those terms, there is a sine x. So you can do what's called common factoring to get from line 1 to line 2. So if you take a sine x out of sine x by division, you're left with 1. Plus, if you take a sine x out of sine x cotangent squared x, you are left with a cotangent squared. And you're kind of hoping to head in this direction. And like I said, I don't know my list of 9 Pythagorean identities very well, but this kind of has the setup. So I'm going to check my Pythagorean identities. There it is. 1 plus cotangent squared theta equals cosecant squared theta. So if you had this on a separate page, instead of having to flip back and forth, you might notice that more readily. I had to flip, that's a bit annoying, so I'm going to replace that with cosecant squared theta. That whole bracket. And then I'm not going to do any flipping because over here I knew that cosecant x is equal to 1 over sine x. So on the left side, cosecant squared x is 1 over sine squared x. Some of you may need to put the 1 down to notice that it's just a fraction multiplied by another fraction. Either way, you could write sine x over sine squared x, or you can say, I noticed that this sine x will cancel it with one of those, and ta-da, they match. Why do they match? Because I will always have them match. If, at least on assessments. If you're in my class, I'm happy. Now, if I didn't have a resource sheet, I couldn't do this question, honestly. If I didn't have a resource sheet, I would have to do this question, or I would have to make a resource sheet as I went along to generate the other Pythagorean identities. So that, unfortunately, is something that is bad for me as a math teacher. So, I'm going to do 1 before 3, only because it's locked in and I don't feel like unlocking it. So let's make this a little tinier. And take a look at this one. Off the top of my head, I can only see one way of doing this question. So I'm going to tackle it that way. This question is X's, so I kind of like it already. So one thing you can do if you like the letters as they are, so if you liked Y, you could have done this with the last questions. You can make your replacements at the same time. However, if you are changing letters, you have to make that your first line so that your communication skills are top notch. So on the right, you don't always start on the right. Yes, we are often starting on the right here. I'm going to turn, this is timesing, I'm going to turn secant into 1 over cos, x in this case, and cosecant into 1 over sine x in this case. Multiplied because these are multiplied, so keep your eye out for that. And I picked those because they really were my only picks. And now I can multiply across the top and I can multiply across the bottom. Just a little note, cos x times sine x is the same thing as sine x times cos x. So if over here I have the bottom reversed, that's okay because it's multiplying. So tan x, I could use this. And cotangent x, I could use this. But instead, because I keep in mind the sines and coses are my friends, I'm going to use these two to replace the tan x and the cotangent x. Just a little tip. So tan x is sine x over cos x, plus cotangent x is cos x over sine x. And then I've got two fractions being added as opposed to multiplied, which means I have to do the 1, 2, 3 thing. Or I have to get a common denominator in some way. Maybe you find this babyish. I quite like it. Otherwise I wouldn't mention it. So cos x times sine x is cos x times sine x. Guess who's a very happy person right now, even if you can't tell? And that is me! Yay, I'm going in the right direction. 2 is in this direction always. You can't mess with that. So that's sine x times sine x, which is sine squared x. Put down the plus sign. 3. Don't say it's babyish if it works. Cos x times cos x is cos squared x, and I shouldn't have to convince you that this is awesome. Pythagorean identity number 1, and they match. And we get that. All right. This one, I really like this one. This one's a good one. Just to mix it up, let's do that. It's x's, so I'm going to do some replacements. So I like sine x on the left. Hey, look at that. I'm starting on the left. I like cos x on the left. I don't like tan on the left. That's from the quotient identities. You can go over to the right if you like, or you can say, no, you know what, that looks very sine and cos-like to me, so I'm going to leave it. Up to you. There are subtle differences. The left is all multiplying, so that means that I can put my 1's down to help me multiply, and I can get sine squared x cos x on the top, the cos x on the bottom. I want to write a little bit less, so because this is all multiplying and dividing and no adding and subtracting, I can cancel a cos x on the top with a cos x on the bottom. Nothing else to clean up. So that ends up with sine squared x over 1 for the left side. So the question is, how do you get the right side to look like the left side? Especially if you've decided that you like the look of this. And the answer is in my list of Pythagorean identities. So 1 minus cos squared x is here, which is why I find it very handy to write 9 of them down. So I can either take the sine squared x that's on the left and turn it into something larger, or I can take the 1 minus cos squared x on the right and turn it into something smaller. And that's my choice. Both choices are just fine. This is my choice because it means that I've been a little more environmentally friendly and I won't have extra lines down here. That's it. That's my choice. That's why I did it. And they match. Don't tell me they match unless they actually match. And we're done. All right, next question. Ew! Okay, so I want you to know that this is the worst question I've seen in the list of 17. Everything else is kind of doable. I'm going to, just out of curiosity, see what's on page 10 here. Oh, those are some awful ones. So what I'm going to do is I'm going to stop this one because I want to keep all the ugly for another question or another video, I guess. That's the word I'm looking for. So I'm going to leave these here. I'm going to guess that some of these are straight out of some of the homework sheets that I've given you. But I'm going to leave them here for the time being, and we will come back to these in a second lesson. So if you need help with these, you'll be provided with a little bit of help. So you have some sheets either in the supplemental booklet I gave you or in the Trig booklet I gave you at the beginning of Trig graphing. Both of those should be listed on the Google site. So that's it for, I'm going to call it part 1. And we'll get at this, which I'll label part 2. So have a nice day.